what I want to do is to first of all paint the problem as difficult as it really is, and perhaps more difficult than you've even thought it was. If it couldn't be more difficult than it perhaps is. And the picture that I'll show again and again in various forms that you've seen yourselves many times is this picture, the picture of existential growth. Excuse me, existential, I mean exponential growth. It's an existential problem, yes. And of course, when we look at this image, what we can see quite clearly is that over thousands of years, the human population has changed a little bit. It's increased. There's bumps in here. This is, of course, an idealization. But what's happened in just the last 500 years, and in fact, truly, really only in the last about 250 years, there's been this rapid uptick. And we've known this for a long time, and there have been studies all the way back into the 1960s worrying about the consequences of population growth. We're not done with this rise, but it probably will top out. Most people estimate that if we just simply leave it alone, it will top out sometime around 2050 at 9 billion. We're almost there now, so we've got a good taste of it. What I want to talk about is what causes these kinds of processes. And how they get exacerbated, and at least some hints as to how we might be able to scale up, and why that's going to be a difficult problem, a problem that we've never really faced before. So exponential growth is in a small sense a runaway process, but what I'm going to mean by runaway is something even larger than this. Exponential growth, of course, is what happens in all reproductive processes. So you have some paramecia in a petri dish full of nutrients. They will grow and grow and grow. If you keep adding nutrients, they'll keep growing. If you enlarge the dish, they'll keep growing. And they will keep growing at a rapid rate. Now, the problem with reproduction, of course, is it's multiplicative. It's exponential. It goes faster and faster and faster. It accelerates over time. So unchecked growth of populations can occur if there's unlimited resources available. But obviously, we live in a world where there's not unlimited resources. We live in a world where there are limits. Surprisingly, we live in a huge world, and yet we've found some of those limits already. Is inevitably accompanied by exponential growth. Is this also the result of not just reproduction, but the fact that you have excess resources? What we see in the living world is where there are resources, growth will take place, and growth will use those resources until they're gone. We as a population are no different than paramecium in this sense, or fruit flies, as I show in the next figure over. What stops it, of course, is we have finite environments. And there are various ways to look at this. And what we see is that there's a number of ways that this happens. On the left here, the standard, what we call logistic curve, is one in which as we approach the point at which we're running out of nutrients, for example, whether it's in the petri dish or in an ecosystem, growth slows, reproduction slows, and other processes take their place. It's only if you continually supply resources that the growth continues to accelerate in this way, as the blue line here is this exponential growth line. The problem is there in living processes and in many of the dynamical social processes we engage in, is there a kind of look ahead that is allowing the system to say, okay, now it's time to slow down? Because if they're not, then you get something like this. This is a microorganism called Daphnia that growing in a medium, in a standard medium, what happens is that Daphnia reproduces and reproduces at this rapid rate and, in fact, way overproduces. It does not recognize, it does not have any signals that it's getting back from its environment that says, okay, things are going to get tough. Reproduction overshoots, and as a result, there's a dieback. Sometimes it can be much more extreme than this. We find this in various predator-prey systems that have gotten disturbed by agriculture moving in and so on. We can find that that the regular feedback mechanisms get disturbed, and we get this kind of sort of skewed effect. It still comes back to the logistic curve to some extent, because this is the steady state, this what you might call the sustained state. And that will be the way it is into the future. But of course, there's an additional problem with human beings, and that is that the amount of resource may be being modified by our very activity itself. Whereas Daphnia does not make more resources, does not dig more resources out of the ground. We do. We find ways to produce more resources and get us, as a result, into a more difficult situation than even Daphnia in its little petri dish. In Bernstein's book, The Birth of Plenty, he quotes Malthus. Thomas Malthus, at the end of the 18th century, made arguments about population growth. He recognized that population growth was exponential. But he says the power of population is infinitely greater than the power of the earth to produce subsistence for men. And what he was saying, in effect, at the beginning of the 19th century, was that populations are beginning to really skyrocket in England. And yet, if you look at how we raise crops, it doesn't seem to keep pace. It doesn't expand at an exponential rate. But paradoxically, soon after Malthus immortalized this grim state of affairs, this prediction, with his essay on the principle of population, which we're talking about here, it abruptly came to an end in Western Europe. That is, he was wrong. He was wrong because something happened. And what happened was the power of the earth to produce subsistence changed. It abruptly and vastly increased. And the growth capacity of the human population was no longer trapped in this grim story that Malthus had suggested. Because the new resource, fossil fuels in various forms, and to some extent even then water resources were being used, began to come on the scene. Helped us smelt metal in large amounts and form machines that could run this fossil fuel. And as a result, this new resource began to increasingly affect the populations. And what we see, it's from this point that populations begin to take off. The point I'm going to make, however, is this acceleration that was provided by this new resource didn't just change population. And that's our real challenge, of course. Beginning in approximately 1840, a number of technological developments coupled European and American socio-ecological systems to a vast untapped reservoir of energy in the form of coal, petroleum, and iron machines capable of converting their energy into mechanical work. This initiated a runaway process that progressively generated more dissipation pathways. I'm going to talk about that in a few minutes. That is, what happens when you do work? You dump waste products, heat oftentimes, into the world in this process, but other kinds of waste products. And we're no different as organisms than machines. We dump our own waste products into the world as well. These new industries multiplied to produce more resources. That is, as we began to use fossil fuels to develop an economy of scale in a variety of ways, it allowed other resources to develop as well that needed to be fueled as well by different sources, by different kinds of resources, by different kinds of metals, by different kinds of creatures, and so on. And so basically what we get is that this produced more resource, but it was able to sustain more people who required more resources, who produced more people that required more resources. And unfortunately, at the same time, all the infrastructure that was involved in this expanded and expanded and expanded. It's not just people, it's not just resources. One of the former researchers of the World Bank, Herman Daly, has had a number of things to say about how we can sustain ourselves in the future. And he makes these three claims. He says, first of all, the alternative to sustainable economy, an ever-growing economy, is biophysically impossible. We can't continue to grow. And just like the Daphnia in the medium it will run out. Our Earth is finite. And since we've been growing at an exponential rate, we're beginning to fill that finite space very rapidly. A second thing, he said, sustainability can be defined in terms of the throughput by determining the environmental capacity for supplying each raw resource and for absorbing the end waste products. So he's not just talking about how much is here, he's talking about how fast things move through the system. And it turns out our economies are now strongly based on the rate of throughput. Rate plays a very, very significant role. What Herman Daly is saying is that rate may be the problem, that we may need to slow things down. The sustainable economy must at some point stop growing. This is a scary thing. Most economists in the world that we live in today require growth. Growth seems to be essential, just like it is having throughput through our own bodies in terms of food and oxygen and so forth. Growth seems to be part of the way we've structured our economy. But what he says is that we can't do this anymore. At some point, we've got to stop. He says, however, that this does not mean that we can stop developing. Development and growth are not mutually exclusive. And here's a diagram from his article that he posted in Scientific American a few years ago that I like. And what he's talking about is time moving along in this direction from left to right. And he's looking at utility, marginal utility. That is, what you might say, what value added you get from what you're doing, what you're producing. And then there's a marginal disutility. That's the costs and benefits, you can think about it as. And he basically is arguing that what's happened is that we're moving to a point in which the marginal disutility is increasing as we dump more resources into the environment and as we deplete scarce resources. And at some point, we hit an economic limit. And that limit occurs when there begins to be more cost than benefit, in effect, and it accumulates. And so you can still offload it, perhaps, toss it into the ocean, bury it underground, all the things that we do. But eventually, that space runs out as well. There's a physiological comparison to this that I want to sort of bring to your attention. And it has to do with what we call metabolic scope. As we exercise and work harder and harder to, say, run up a hill or bicycle. I saw people bicycling up this hill that astounded me that anybody could do, but I guess you guys are stronger than we are in the West. What happens is you run into a point in which your heart rate goes up, your breathing rate goes up. And you bring more oxygen and glucose into your system, and glycogen gets released into your muscles, and you're able to sustain higher and higher levels of metabolic activity. But at some point, the increase in the level of oxygen you're bringing in by breathing harder and pumping your blood faster, it takes energy to do those things. And that energy is, of course, a fraction of the oxygen that you're bringing in. At some point, you reach a crossover point. This is called the metabolic scope, in which no amount of breathing faster provides any marginal utility. There's no amount of increasing the rate of your breathing can bring more in because now it's costing more to breathe to do this. Now, this turns out to be a feature that we see all the time, and we're beginning to run up against this in other ways. For example, it used to be that how many fish you could bring in had to do with how big your fishing fleet was, or how big your nets were, and so on. But at some point, you reach the marginal disutility point, in which expanding the technology to do this simply does not bring in more. Although you can increase the number of boats that are fishing, at some point they all begin to diminish in the utility of this process. Part of the issue here has to do with a very simple, basic thermodynamic principle. and I want to sort of play this out so you get a sense of it. This is my simple way of sort of caricaturing this principle that we call the second law of thermodynamics. I'm sure you've heard the concept of entropy. A second law of thermodynamics is also stated as that whenever you do work or you make any change in the physical world, entropy increases. Entropy can be understood as disorder, or more accurately, the inability to do work, the loss of the ability to do work. But what's interesting is in doing work, you lose the ability to do more work over time. Things spontaneously fall into a mess. It takes work to organize things, to build structures. It takes work. One of the things that we can do oftentimes, as this yellow line suggests here, is that we can take advantage of the spontaneous tendency for disorder to accumulate over time, to do a little bit of work, to take someplace else in the world and do a little orderly work, or to push things against the tendency. All of life works this way, of course. We're able to take in oxygen and food, as I talked about a minute ago, and do this kind of work. It turns out that this happens spontaneously in a variety of ways. And one of the things that we've begun to learn about living processes is they use this principle in a kind of simplified way. And I want to give you the simplest version of it that's familiar to everybody, and that's a whirlpool. A whirlpool forms a regular pattern. And it's a little bit surprising to see this nice, neat regularity form spontaneously without me having to do any work as I pull the plug in my bathtub. But in fact, what's doing work, of course, is the water draining downhill, going from a higher position to a lower position, a higher energy position to a lower energy position. It's the work of going down the drain that actually organizes the whirlpool. And in fact, a lot of life has to do with using these spontaneous tendencies to organize by work taking place. The problem with this is that, for example, if you want to drain your bathtub a little slower, all you really have to do is disturb the whirlpool, and it will drain slower. The whirlpool forms to drain water faster out of the bathtub. It's not trying to drain water faster. It's just that water organizes in such a way that it moves faster from a higher energy state to a lower energy state. A lot of spontaneous order shows up in the world by this kind of a process. All work is about organizing in some way or another against the grain. The problem is that in these kinds of processes, it actually speeds up the production of entropy. It speeds up the second law to some extent. And this has been called the maximum entropy production principle. And it's one of the things I want to come back to because that's one of our problems. As we have used regularizing processes, as we have done work to regularize our world, one of the things that's happened is that we're producing entropy faster than more simple systems. We produce more heat than you would imagine possible if you were to do it by simpler means. So as we move towards more and more complex forms of producing societies, we're actually generating heat at a faster and faster rate. We're generating waste at a faster and faster rate. And even if this happens spontaneously, and I'm going to talk about a number of spontaneous coupled processes like this, it does that. We don't have to be doing the work. That work can happen spontaneously to do this to us. These are two statements of this, one from a theorist early on in the history of biophysics, a man named Lasse. He says, evolution occurs in such a direction as to make the total energy flux through a system maximum along all the systems I'm having trouble saying it here, all the systems compatible with the existing constraints. In other words, what he says is that if you leave systems alone, what they will do is they will maximize the breakdown of the energy that's available to them. In the same way that an organism population that's reproducing maximizes as rapidly as it can by reproducing rapidly the use of that resource. And finally, and this is one of the challenges that we have, Howard Odum, an ecologist from the last generation, makes this claim. He says the system using the greatest, if you have a number of systems, we talked about groups, now I want to talk about physical systems and biological systems, and of course, you might say corporate systems and so on. The system using the greatest amount of energy and consuming it in the most efficient way survives in the competition with other systems. Another way to put it is that if you're using up the resources faster than your neighbor, they will probably die before you do. That's unfortunately a problem that we face. Let me give you a couple of more complicated examples of this kind of process so you can get a sense that it's not something that we have to do. It can happen spontaneously. And it's the spontaneous nature of this that I'm worried about. This is something called Rayleigh-Benard convection cells. What you see here is a dish of oil about 2 millimeters thick. It's very, very, very thin sheet of oil. You heat it from the bottom, and normally as you heat a liquid, of course, the heat convects up through the system, and it's conducted out of the system by just molecules bumping into each other, so to speak, and conducted out. But as the heat goes hotter and hotter, conduction of heat, like through a liquid or through a solid, is not fast enough to unload the heat into the environment as fast as it needs to go. So what happens is the heat within the oil heats up faster and faster and faster, faster than it can give it up. As a result, what happens is the hottest oil is now of lower density. The molecules bumping into each other decrease the density, which decreases the weight. And the heavier oil that's cooler on top begins to fall. And it creates what we call convection cells, where there's falling bits of oil and rising bits of oil. What happens is, as it heats up hotter and hotter and hotter, it organizes. Now, oil doesn't become hexagonal spontaneously because of something about the oil. It becomes hexagonal because this is the most efficient way to dump the heat into the world. What happens is that there's rising hot oil in the center of each hexagon and cool oil dropping from the outside, driving the system beyond the point at which it can, in a spontaneous, simple way, by conduction, just give off the heat. Pushing it beyond a threshold allows it to organize itself. And it organizes itself in a way that, in a sense, couples the heat dissipation throughout the system. And it's this kind of coupling process that I want to talk about next. Before I do that, I just want to show you an example of this so you realize that this is something fairly straightforward and simple, but it's nice to see it. And in this particular example, this is oil with a little bit of aluminum flex in it that's going to be poured into this heated pan. You can do this yourself. I don't recommend it because it has to be here heated to 350 degrees. But if you've got a nice flat pan, and it needs to be a flat pan and a very fairly flat heating surface, so you can see what happens here. As it heats up, it begins, and you've probably seen this sometimes in your kitchen, as it heats up, it begins to organize. Now, it's not quite so neat as I just showed you because, in part, the pan itself has irregularities. And so some areas are hotter than others. But now, if you look close up, you can see the particles of aluminum rising up in the center and falling down the outside. It organizes itself in order to pass the energy through it at the fastest possible rate. Now, in thinking about this process, I've been interested in how thermodynamic processes, and we've been talking about this, link to those processes that get organized, like I just described to you. And then, finally, how they get organized into living processes. And so I came up with 3 ways of talking about this. The terms are not important, but you can think about them as kind of a nested problem. The first is the thermodynamic problem of the second law. That is just the dissipation of excess energies, the way that energies equalize in the world. But if you push it in certain ways, you can produce what sometimes is called self-organization. I like the term morphodynamics. It's a dynamics that produces forms and regularities, just like those hexagonal cells. And if these are organized in a particular way, you get living processes that are order-producing. They do work to produce structure, but they also maintain that structure. And one of the problems with self-organizing processes, and this is going to be crucial to what I say next, is that they produce entropy, they produce waste, they produce heat faster than normal, faster than simple thermodynamic processes. And as a result, if you've got a finite resource that's driving it, it will use up that resource faster and faster and faster. It's the fastest way to dissipate heat, for example. Living systems can't do that. Living systems have to sustain. Living systems have to produce order, so they have to do this kind of work. But they can't produce order in a way that completely dissipates the source that it relies on. Unfortunately, populations like the Daphnia that I showed you can come close to making a mistake in that respect. That is, if they don't have a way of assessing how they're utilizing their resource and monitoring their growth processes with respect to that, they sort of overshoot. So what I want to say now is that when we look at our current situation, the situation that begins in the 1830s and 40s, one of the things that's happening is that the total amount of resource in the system has been pumped in from a new source. What's that source? Well, that source is actually what life sequestered over billions of years. Life, as I've just mentioned to you, has a process of generating order and generating organization. But it does so in a way that also sequesters a little of it. And in the course of dying, organisms getting buried have not fully broken down the molecules that they produced. There's a little bit of work potential left there. It was accumulated over billions of years in the fossilized subterranean areas of the Earth that we now are using as fossil fuels, whether it's coal or oil and so on. So prior to living processes, the sun hit the Earth and, in effect, was absorbed into the rock and then re-radiated into space. With life, life captured some of it, sequestered it, ran it through lots of different self-organizing lines to produce its order, and sequestered a little bit of it. Didn't allow it to completely dissipate. And by not allowing it to completely dissipate, what happened then, of course, is that it saved a little bit of savings, you might think about it as. Unfortunately, what happened in the 1800s is we learned how to tap into what life has been saving for some odd billion years. And where life didn't dissipate it all at once, in each generation, we're now dissipating it, taking that 3 billion years of unused potential and dissipating it as fast as possible. And it might make it obvious that this is going to be a source of order, a source of regularity, a source of building structure, which is what all our civilization is about these days. But in building that order and that sophistication, we're also ramping up this process. We're speeding up the process because it's a self-organizing or morphodynamic process. So one of the things that's happened in this process, and I won't sort of read through all of this, is that we've begun to take what life sustainably was sequestering over a long period of time. Incidentally, not on purpose, living things just simply sustain as long as they can so that they don't exhaust their resources. And as a result, a little bit gets saved. By us using it up real fast right now, we're effectively using up the energy of the sunlight of 2.5 billion years of accumulated sunlight, which was hitting the Earth and didn't get re-radiated into space. So the difference between the process in which sunlight hitting the Earth causes living processes to reproduce, living processes will, like that logistic curve I began with, at some point stabilize out. And they'll stabilize to the point that they're taking in energy and dissipating energy at a rate that is no faster than it's coming in. They can't push beyond that. But when you find a new source of energy, in addition to the constant throughput that's coming in from the sun, you can push this system far beyond the rate that was normally happening with the rest of life. And that's, of course, what we've been doing for the past 150 to 200 years. As a result, two things have happened. Since this rate is constant, living processes stabilized out to take it in and give off waste products at a fairly stable rate. It's still costly, it still produces waste products, but it's always being replenished. Living processes, to be stable, had to stabilize that process. But if you now throw in extra energy, you set the system off in a very different way. And so what we've been doing over the past 150 years is, in a sense, superimposing an extra source of work that, of course, produces extra heat, extra waste. And that's our problem. And this shouldn't be news, of course. The key is we have to figure out how to regulate this flow. It's not that it couldn't be regulated. If it was regulated in such a way that it was moving through in a sustainable rate, a rate at which it's not used faster than it can be found. Unfortunately, this is a finite resource. And not at a rate that produces a throughput that produces too much waste to be taken up by the environment, then in fact it could be useful. And in fact, we find this in life, a process similar to this, a kind of temporary runaway process, a temporary acceleration in what we call ecological succession. If a forest is burned down, for example, one of the things that happens is many of the nutrients are in the soil but not immediately available. And what happens is species that are less efficient begin the process, grasses and so on, that can rapidly utilize processes, but don't sustain well. And over time, what happens is that in ecological succession, more and more of the throughput of energy is held in place in the ecosystem. So that what we say is that more and more of the biomass is stable for longer periods of time. It's slowed down. In this process, what happens is that early on it's reproducing quite rapidly. And as it becomes stable, as it begins to hit that plateau on the logistic curve, what happens is that everything begins to hit a rate that's appropriate to input and output. And of course, the problem is what happens when you pour new resources into it, which is what we've done. You shift this balance. The problem is if it's a finite resource, you will make it unbalanced for a period of time. It'll have to fall back into its original state, a little bit like that Daphnia story that I showed you previously. A way to think about this process and how it can link with other processes has to do with this idea of autocatalysis or reciprocal catalysis. A catalyst is a molecule that interacts with another molecule to increase the rate and probability of a chemical reaction. The digestive enzymes in your gut are doing this. They're aiding chemical reactions, but they themselves don't get used up into it. So here I show an image of E, a molecule whose shape fits into this little sort of notch that speeds up the chemical reaction of splitting B and C. Autocatalysis or reciprocal catalysis occurs when you get a kind of a you scratch my back, I'll scratch your back nature of this process, in which producing one catalyst to produce one reaction produces a second catalyst, produces a second reaction, which by a series of steps, maybe in this case only two, produces another version of the first catalyst again. This is a runaway process. It's a runaway process because every time you cycle around this, you may start out with one catalyst. Since the catalyst itself doesn't break down in the process, by the time one cycle has gone by, you have two. And as it goes around again, you have 4. As it goes around again, you have 8. And that's of each of these. And you can see that this is a little bit like reproduction. And in fact, many people have compared this to reproductive processes. But it does the same thing. It has this exponential growth feature. As a result, catalytic processes very rapidly speed up chemical processes. The problem is that catalytic processes can also couple with each other, because if something produces a side product that is itself a catalyst, that catalyst can do more than one thing. And if catalytic systems get coupled, where one catalytic cycle aids a second catalytic cycle, it can begin to recruit a third one. We see this idea of self-organizing processes recruiting each other in things we call vortex streets. If you produce one vortex, because it produces an asymmetric rotation, in this case of a gas, it will induce the contrary rotation next to it, and you get a coupled series. What people have shown is that coupled chemical series of catalysts occur in organisms all the time. Cycles of catalytic activities that speed up and make more efficient what goes on in the body. The problem is that when you couple runaway processes like this, they speed up each other. And what I want to say is that that's the problem I think we face now, is that we have begun to see how all of the various production processes that we've been utilizing this energy for have become coupled. And each of them has a runaway effect, but they therefore have a collective runaway effect. And so if you're depleting one resource to do one process, it can capture the resources next door to it, so to speak, to speed up another process. And so what we see is the availability of an energy resource that can be continually scaled up. We can get more and more fuel from the earth over time, at least we could for a long period of time. This can meet almost any need to produce work. But the fact is that then that can increase our agricultural yield by using fossil fuels. Agricultural yield, it can increase mobility and good transports. It can increase global wealth and individual wealth and asymmetry of wealth. Because each of these are catalyzed by each other. It can increase our ability to concentrate people in an area because we can produce lots of resources and bring them to people where they don't have to be where the resources are produced. And of course, this has produced cities, but it's also produced our global exchange system. Because of all these processes of accelerating and making more efficient these other features, of course, it produces the possibility to have more people. But more people, therefore, need more resources. You need to scale up the process. As the population goes up and moves and concentrates, one of the other things that happens is we can use these resources to decrease mortality rates, for example. Populations, as they go up in numbers, also demand more resources. But they demand not just more fossil fuels, they demand more arable land, more water, more heavy metals of various kinds, more precious materials, scarce resources from a variety of ways. And what we see as a result is, although I showed you the one curve, the population curve, what we see is throughout the world, there's coupled curves. All of these curves are coupled, and they're all exponential in one way or another. Some of them are already on the decline, many on the increase. So I just show a few here that give you an idea of this sort of coupling. And that coupling is in various ways, so it's not just one resource. As one resource is being used up, it also allows us to say, oh, hey, there's another resource that can fill in a gap. And another resource, and what we see is that they're all increasing. As population goes up, a number of other things happen. One of the things that happens is the GDP increases. Numbers of people increase, but the amount of production of materials goes up to meet that need, but that need being met now allows the need to grow as populations grow, as more materials grow. What I want to talk about here is this is a runaway process because a single catalyzing process can catalyze linkage with others. And our problem is not that we're just growing fast, Not that we're just producing a lot of heat into the atmosphere, dumping a lot of carbon, but we're also using all of the available resources we can faster and faster and faster. That's the sustainability problem. It's not just keeping us fed. It's the fact that we're using everything faster and we're dumping the waste products faster and faster in all ways. So that you may buy an electric car to have more efficient use of, in a sense, energy per distance. On the other hand, that electric car is going to utilize rare earth metals, and they're going to sustain in the environment as waste products for a long period of time. The full lifetime of that may not, in effect, give you the marginal utility in the long run that we want, because it couples with many, many processes. And it's this coupling of runaway processes that I think is most interesting. So one of the things that's happened, of course, in this process is we get environmental degradation and we get resource depletion. And we begin to shift to petroleum products to do all kinds of other things. Although you drive your car possibly with electricity, as I do these days, the tires of my car are all made with petroleum products. The dashboard of my car is made with petroleum products. Many of our clothing and building components are made with petroleum products. Once we become good at extracting it, we become good at also utilizing it all kinds of ways, and we need more of it for all of those purposes. In a sense, the catalytic processes tend to attract each other, and I think that's our challenge. Well, of course, there's one other runaway process, and that's the heat process. The fact that we know that as we heat up the earth, it's quite likely that it will be a runaway process of the same sort. And we don't know where its logistic curve will flatten out, whether it will flatten out at a stage that is still livable or at a stage that's not so livable for us. This is yet another coupled piece, because now the whole environment is coupled into this runaway process that we've created. The question I want to ask is, maximum entropy production processes like this, that have this kind of spontaneous tendency to couple and drive each other and to recruit each other, so to speak, are they unstoppable? I think they're pretty close, and I think that's our biggest challenge here. Now, we know that they're unstoppable in the that they're stoppable in the following sense, that when energy input drops below a certain level, that is, if we run out of fossil fuels in the next 50, 70 years, however long it will take, the autocatalytic linkages that are driven by it won't be sustainable. It's not just that we won't be able to drive our cars and heat our houses. It's that we won't be able to build our tires, create our glasses, construct our various computing devices, and so on and so forth, because we have diversified its use so radically. But that also means that each of those processes, whether it's making tires or making computer screens, is also a demand on oil as well. It says, don't cut me off because you need me. So what we've done is we've created, by diversifying this use, we've also created lots of, you might say, sinks that are pulling it and driving it more, making it a much harder to stop process, much harder to slow. And in fact, if it slows to a complete stop, what happens is, like the Daphnia, there will be a collapse. A lot of the support, the infrastructure that's been produced this way, will collapse around us. And that's our biggest fear, of course. So in socioeconomic terms, socio-ecological terms, this implies the complex infrastructure of most of our technology will degrade. Not just that stuff that is directly driven by fossil fuels, but this entire infrastructure that's indirectly driven by it. So to keep these linked runaway processes from fully depleting this gradient, which is happening faster and faster and faster, as we know, it's necessary to do some kind of constant countervailing work. These are processes that are doing work. And these are processes that will spontaneously replace each other. If I stop a process here, another process is there to drain some of the extra resources. I like to compare this to this classic myth of the Hydra. These kind of linked cycles we call hypercycles. The Hydra in the classic myth was one in which if one neck was cut off, one head was cut off, it grew back 2 heads. I think that's our challenge. There are lots of wonderful programs in the world that have cut off some of the heads, whether it has to do with shifting over from fossil fuels to drive cars to electricity, or saving rainforests, or using sustainable farming methods, and so on. Each of them is, in a sense, one head of this Hydra. The problem is, to kill the Hydra, or to control the Hydra, or to domesticate the Hydra, we have to get the whole thing. And that's, I think, our challenge. How do you get to the whole thing? Well, here is the problem. Is it that resistance is futile? Does it have so much momentum that we can't stop it? Because these processes are accelerating, as you know, any accelerating process gets harder and harder to stop. The faster it accelerates, the more momentum it develops, the more effort, the more work it takes to resist that process. Right now, we're at a stage in which it's accelerated to an incredibly maximum rate. The question is, what kind of work can be exerted to stop it, or to slow it, or to bring it to a sustainable level? My fear is that doing so legislatively may not succeed. And this is my great worry. I think we do a good job of it, and ideally we would like to be able to scale up the sort of small group logic for the whole world. The question is, how could we possibly do that? In order to be sustainable, we need to do something like that. The question is, are the countervailing forces so strong that it's hard to do that? What's necessary to do that? My argument is that what you need is a countervailing runaway process. In other words, an accelerating process can only be stopped by something that is, in a sense, equal and opposite to it in strength. What might that be? How might we do that? Well, it will have to be a process that also has this kind of acceleration feature. It's not just scaling up in a one-to-one way. We've got to scale things up in a sort of accelerating way. That's our problem, because time is running out. So I think that only a countervailing runaway process can have the capacity to match the powerful self-amplifying dynamics of this Hydra effect that we are dealing with. The question I have is, what kind of process is this? I think there's lots of countervailing processes at different levels, and it may be that all of them need to be running at the same time. We're seeing a lot of this happening at the level of education, for example, educating people around the world, giving women power in different places in the world, seems to be slowing some of these processes, particularly the reproductive process, interestingly enough. Birth rates are going down, marriages are being delayed or postponed entirely. There's a shift in the age pyramid in which the young become a smaller fraction of the population over time. A number of things happen, but they happen slowly. They happen over generations. And although these countervailing forces might have played a role, they're probably happening too slow. So what I want to do is I'm going to just show this picture here to show these are some of these what we call demographic trends. These are all happening, I think, as a consequence of this problem. That is, birth rates are changing. We are decreasing a little bit our use of fossil fuels per capita, which is interesting because we're doing it at such a massive scale. We can be more efficient at it, but that doesn't mean that they will stay around forever. Fossil fuels become a transitional fuel source. Let me just show one example here that's hopeful but too slow. Here we see birth rates and death rates over time. And what we see is that as technology moves in, the mortality rate drops, particularly at infant levels. At childhood levels, mortality drops. And eventually birth rates drop as well. but birth rates take about a generation longer to drop than death rates do. The result is, even though both birth rates are dropping and the death rates are dropping, people are living a little bit longer, but still we're not replacing the population still grows. So what we see is that the population will still grow for quite a period of time. It's estimated, as I said before, that about 2050 it'll begin to decline again. I think that the answer to this has to do with the problem itself. And I want to give, it's a somewhat science fiction-y flip answer. This is just a list of technological developments. And the same thing has happened with respect to knowledge and technological developments. They have increased at a rate that's exponential as well. So this is the population curve that I showed you at the very beginning. Here we see the years down at the bottom, 1900 to 2000, and where we are here. And what we see is that the rate of discovery of new tools, new technologies, new scientific innovations has also increased. And that's, I think, the positive sign here. It's also involved in a runaway process. The fact that we can have these conversations, that we can use satellite technologies to assess what's going on and so on, is telling us that there's something else that's ramping up at the same time as all of these other problems are ramping up. Our ability to look at them, to follow them, to understand them, and to predict the consequences. What we now have is pretty good predictions of the consequences. We just don't know how to politically solve those problems. So I want to make one sort of crazy suggestion, particularly to you young people. There is a new runaway process that has appeared in the world. That runaway process is what we call things going viral. The fact that we have a global communication system that can communicate technological advances, intellectual advances, ideas about how groups can be stabilized, how they can be, how large-scale cooperative relationships can be established, and how they might be even automated electronically, organized not by humans alone, but by being able to track large numbers of processes. I suspect that the technologies that we have, because they are also going viral, so to speak, they are also runaway processes, are really the only ways that we have to resolve this. And that we probably have the possibility of succeeding at it. But it's not just technologies, it's not just laws, it's not just international agreements. It's also belief systems. One of the things that David was talking about was, in effect, the purposiveness, the intentionality of groups. We have the possibility, and it's beginning to expand through the internet, of shared intentionality. One of the questions is, it may well be that the way into this process is that the global industrial economy is in fact becoming more and more controlled by the information economy. And the information economy itself has this kind of runaway logic behind it. Not everything does a runaway, but it looks as though it has this same kind of logic. So my suspicion is that this grandchild of the Industrial Revolution may provide the dynamical counterpart to this ecological economic problem. That is, by expanding one system, the control system, we can begin to control the other. I end with this brief note. I won't go into the details, except to say that living processes do it this way. Living processes are run by information, but they are also runaway processes. But they're runaway processes that have used their information systems to, in a sense, balance the runaway, to sustain this process. In one sense, it brings to mind the concept, you mentioned Lovelock at the beginning of your talk. It brings to mind the concept of Gaia, of a one-world life. The organisms on this earth do not act like an organism today. They're an enlarged ecosystem that is, in fact, being heavily impacted. But in one sense, in order to have a sustainable world, a sustainable living world, it needs to be more like an organism, not just like an ecosystem. And that means that we have to, in effect, create Gaia. And that means that our information, our minds, our intentions are part of that process. Thank you.